We're very happy to have Jeff Cheeger from
Yeah, so it's always a pleasure to be back in Stony Brook. So I was asked by Mark to, as I understand it, to give some kind of survey, which is a little bit complementary to the main theme of the conference. So I'm going to talk about Ricci curvature, which does, of course, have a strong connection to special holonomy, but then special holonomy is much more special. So I want to, as it says, review some recent progress and even mention some less recent stuff and some problems that are still open. So I won't really give any details and very little indication of proofs. There is this connection that in all cases except Kahler, where you might want to assume bounded Ricci anyway, they are Einstein. So that's a reason why you might be interested in structure theory for Ricci curvature, even if you're interested primarily in special holonomy. And there have been some applications of the general structure theory, and on the other hand, some of the questions that are open in the more general case are still, as I understand it, open even for special holonomy. So they suggest some things which one could work on. So the general context for most of the talk is consider Gromov-Hausdorff limits with or without special holonomy with bounded Ricci curvature. In the first part, we'll also make non-collapsing assumption, which is the volume of, say, a unit ball has a definite lower bound for the manifolds in this sequence, and at various points will drop one or will weaken the bounded Ricci to a lower bound on Ricci, and later we'll drop the non-collapsing assumption. So let me remind you that if we assume just a lower bound, uniform lower bound on the manifolds in our sequence, then we have this notion of Gromov-Hausdorff convergence, and we have Gromov's compactness theorem. So any reasonably controlled sequence has a convergent subsequence. So we can talk about limit spaces, and given a limit space, there's a notion of tangent cone at every point. And by that, we consider a rescaling sequence. So we put the inverse in there, so we're blowing up the metric. We take a pointed limit, and by Gromov's compactness theorem, after passing to a subsequence, there'll be at least one such limit, and we call any such thing a tangent cone. So this is a reflection of the infinitesimal structure of our limit space. It's natural to ask, what could we say about it? So examples show that they always exist, but need not be. Examples show they need not be unique. But an important aspect of the structure theory in the non-collapse case is that every tangent cone is a metric cone. And the cross-section is a length space, and the diameter is at most pi. And if it's equal to pi, then the cone will split off at least one line, and so on. So now we can talk about the regular set, by which we mean the set where some tangent cone is isometric to Euclidean space. So I thought I had fixed this, but I didn't. And so we're talking now about the non-collapse case at this time. So if one tangent cone is isometric to Rn, then everyone is. In fact, this is basically a consequence of an Epsilon regularity theorem of Mike Anderson. And however, if we're just assuming this is the lower bound, then the regular set need not be open. You could think of a two-dimensional convex surface with a countable dense set of conical points, most of which would be very weakly conical. So the singular set in that case would actually be dense. But even in that case, if you basically consider the points where the volume of the tangent cone is sufficiently close to being what it would be in Euclidean space, then again, basically by a theorem of Mike, those points are manifold points, and in fact, this epsilon regular set, let's call it, is by Euler equivalent to a smooth Riemannian manifold. Now, so let's consider the singular set, still only with a lower bound on Ricci, which by definition is the complement of the regular set. And this has a natural filtration where the kth element of the filtration, sometimes it's called a stratum, but really it's the differences between two of these elements of the filtration that probably should be called strata anyway. So the kth SK consists of those points for which no tangent cone splits off RK plus 1 isometrically. And in the sense of Hausdorff dimension, in this theory that Kolding and I developed, one of the results was that the dimension of SK is at most K. So here you could think, pretend that this limit space is a simplicial complex to get a feeling for this, and then if you're on, let's say, an interior point of a K-simplex and you expand the metric, then in the K-simplex direction you'll get an RK, and in the normal direction there's a normal cone, which just becomes some cone. In that case, of course, it's unique. So this is like consistent with the idea that the K-skeleton of a simplicial complex has dimension at most K. So this sort of technology and geometric analysis was pioneered by some of the great pioneers of the subject, DeGiorgi, Federer, Fleming, Holmgren, and Schoen and Uhlenbeck, initially in the context of minimal submanifolds, and subsequently by Schoen and Uhlenbeck in the context of harmonic maps. So this part of the theory works in much the same way. The crucial point is that there's a monotone quantity, which in this case, in these cases, it's an energy density. The monotonicity, let's say, in this case is basically what's called the cone inequality, and here it's a consequence of the Bishop-Gromov theorem. So it's monotone. The non-collapsing assumption in our case says that there's an a priori bound on it, and it's what I would call, I don't know if this is standard, coercive, which in this context means that if this energy, this volume energy, behaves from the standpoint of volume almost as if you were looking at a cone, then from the standpoint of the metric, in the Gromov-Hausdorff sense, it will also, the space will be almost a cone. So there's, in all of these cases, you could say there's an a priori bounded monotone quantity which is coercive. Okay. So now if the two-sided bound holds, then the singular set in that case actually must be closed. This again is basically a consequence of an epsilon regularity theorem of Mike. And in the bounded Ricci case, the regular part then will be open, and in suitable harmonic coordinates, it will actually be a C1 alpha Riemannian manifold. And if, for example, the metrics are Einstein, then you could say C infinity. Okay, so that's the regular part. As I said, the crucial thing here is epsilon regularity theorem of Mike, which says that if in this bounded Ricci case the volume is almost maximal, then say on a ball of half the size, the metric is actually smooth, either C1 alpha, or in the Einstein case, C infinity. Okay, so this is proved by a very artful blow-up argument, which technique has proved useful subsequently as well. So as previously mentioned, connection between special holonomy and Ricci curvature is except for the general Kahler case, where you often might want to assume that you had either a lower or two-sided bound on Ricci anyway. Manifolds with special holonomy are automatically Einstein, and in the more exotic cases, they're actually Ricci flat. And one thing one can say is that there's a distinguished, in all of these cases, there's a distinguished parallel n-4 form, and the metric is, the trace-free part is anti-self-dual in this sense, that the trace-free part of the curvature, which is some kind of 2 form, wedged with this n-4 form, so this gives an n-2 form, and with suitable conventions, that's star of the curvature with the minus sign. So in particular, if P1 denotes the first Pontryagin class, then it has the consequence that in these cases, the L2 norm of the curvature is bounded by a topological invariant. So basically, I would say this discussion is due to Simon Solomon, and there's a kind of also a discussion in my paper with Tien on special holonomy from 2005. So in that paper, this is kind of background. It's not the latest, as we'll see. But so in that paper, we showed that in the non-collapse case for limits with bounded Ricci and special holonomy, the singular set actually had codimension 4. We were able to show that by a suitable epsilon regularity theorem together with the L2 bound, and that the bounded subsets of the singular set are n-4 rectifiable. This means Hausdorff measure with a definite bound on the Hausdorff measure. So that's stronger than just saying the Hausdorff codimension is 4. And at almost every point, tangent cones are unique and of orbifold type. So we'll see a striking generalization of this recent generalization below. So just to remind you what rectifiable means, so we'll say a space is, say, K rectifiable with respect to a measure if there's a measurable decomposition of almost all of the space with respect to this measure, with the property that each of these sets is by Lipschitz to a subset of Rk. So it's kind of like the measurable version of being a manifold, but of course it's not quite being a manifold. And this kind of issue seems to me maybe wasn't given the so there were results like this in the previously mentioned cases like minimal surfaces and harmonic maps, and you wouldn't see, at least I didn't see so much what one might have thought would get more attention, namely, can you say more? That is to what extent can you say the singular set is actually a manifold? So this was kind of the standard thing that people said. And then one could add this further condition on the measure that restricted to this set, it basically looks like a function times Lebesgue measure pushed back by the inverse map. So just as a complement to what I said here, there was an earlier paper of mine which actually talked about LP curvature bounds, just the lower bound on Ricci, and proved rectifiability of the singular set, but there were some exceptional, possibly points where the relevant epsilon regularity theorem, the proof in that paper didn't work. So this condition about being exceptional or not referred to the particular tangent cone at the point. So in the normal direction, you would have S3, the cone on some S3 modulo gamma, and maybe that had to have a non-zero Chern-Simons invariant to get a contradiction in the kind of slicing argument that we were using at that time. In the Kahler case, that was easier because instead of a Chern-Simons associated to, you could think eta invariant or Pontryagin class, in the Kahler case it was really like more like an Euler characteristic, so there weren't any exceptions. Maybe I'll come back eventually. It's kind of technical, but so then more recently in the Kahler Einstein case, by a rather different argument, Donaldson and Son showed in particular that the tangent cone is unique and the epsilon regularity theorem corresponding with no exceptions. And they prove much more. Well, let's see. I'm kind of a little bit mixing up in my mind the epsilon regularity and tangent cone uniqueness. So there was another paper of Donaldson and Shushang Chen that I'll get to a little bit later. Okay, so in any case, in the Kahler Einstein case, as I understand it, right, the tangent cone is unique at all points. And they proved much more in that paper, which for reasons of time and lack of knowledge, I won't be able to go into. So now, another recent result, again in the non-collapsing case with a two-sided bound on Ricci, is that the singular set has codimension 4. So with just a lower bound, of course, this wouldn't be true because you could have a cone in the form of a paper cup that had a sharp point, and then there's such a two-dimensional limit space, you could round it off so it would be a limit with actually positive curvature near the rounded off cone point. So the singular set can be clearly codimension 2 with just a lower bound on Ricci, but it turned out, so this was a long-standing problem, that actually just in the non-collapsing case with a two-sided bound on Ricci, it's codimension 4. So I'll get to the history of this in a moment. And in that same paper, in dimension 4, there was a finiteness, diffeomorphism finiteness theorem. So there you could say more. And as a consequence of the diffeomorphism finiteness, there is actually an a priori L2 bound on the curvature. So it means if you fix, say, the diameter and a lower bound on volume, so this kind of looks like the more classical finiteness theorem in general if you had a bound on the sectional curvature, but in this special circumstance, it's enough to bound the Ricci curvature. And if we took limit spaces, then there would be only a definite number of singular points, and the metric is of orbifold type. So this is special to dimension 4. It wouldn't be true, at least the diffeomorphism finiteness part, in higher dimensions. So those results in dimension 4, as well as the codimension 4 part, which I think I may have omitted from the transparency. So all of this was conjectured by Mike in his ICM paper from 1993. And I guess if you assumed, so there were in addition to Mike, Nakajima was someone else who was doing this pioneering work. It was understood with an L2 bound assumed, then you could get these conclusions, and the singularities would be actually of orbifold type, which definitely takes some more arguing that the metric is at the singularities on a limit space actually is a quotient of a smooth thing. And of course, what's special about dimension 4, absolutely crucial, is that if you have a bound on, if you assume a bound on Ricci, then the Chern-Gauss-Bonnet form bounds the norm of the full curvature tensor. So that's a crucial thing in dimension 4, which you can't use in higher dimensions. So maybe I'll come back to mentioning that as well. So now we come to a recent and really spectacular result, which is by this guy, Wenxue Zhang, and our friend Aaron Neighbor. This guy, I think, is still a graduate student in Beijing, as I understand it. So if you have non-collapsing and a two-sided bound on Ricci, with just those assumptions, but now in general, so we know we knew from what Aaron and I did that the singular set had Hausdorff codimension 4. I mean, you can actually say codimension 4 in a stronger sense, like Minkowski dimension, for example, or even packing dimension, but let's leave that aside. But now the assertion is that in dimension n minus 4, the Hausdorff measure is actually finite, and in addition, in the sense that we talked about, but now with respect to n minus 4 dimensional Hausdorff measure, the singular set is rectifiable. So this is, and in addition, there's an a priori bound, which we just mentioned in dimension 4, on the L2 norm of the curvature, now in arbitrary dimensions. And there are actually also corresponding results for these for lower strata, but you have to, so to say, truncate the strata appropriately. So if you look at the strata as defined previously, you have to assume, so they're defined by saying there's no tangent cone that splits off RK plus 1. So if you strengthen that condition to say actually all tangent cones are a definite amount away from splitting off RK plus 1, then this finiteness would apply also to the lower strata. So this is quite something. And the first part, I guess, was conjectured in this paper. Of course, it wasn't known that the singular set was codimension 4, and the L2 part was conjectured in the codimension 4 paper with Aaron. And it seems now that actually this discussion can be extended to just a lower bound on Ricci in the non-collapsed case. But we're still checking the argument, so this is just like a bulletin. This is certainly not written yet. So in the Kahler Einstein case, actually, it's known that this orbifold structure along, let's say, the top stratum of the singular set actually extends. So this is Tien, and I think Lee is actually the co-author. I don't know who that is. I don't know. Maybe Simon can say whether this also follows from the work of Donaldson and Son, the orbifolds. I mean, they have a lot of information, but I don't know if it includes this or not. Okay, well, that's I didn't mention, but that's a good open problem if it's not to see how it relates to their work. So in this 2005 paper, the orbifold structure was conjectured explicitly for special holonomy and off a subset of codimension 6, but this is why it's codimension 6 is because some of the strata in the special holonomy case, like the splittings, and for example, in the Kahler case, the splittings of the tangent cones are actually complex splittings, so some of the strata are empty. Here by strata, I mean the difference between two of the SKs. So I believe, right, that this is still open. And so maybe that's a good problem. And even it's possible that something like this holds just with bounded Ricci. So maybe before we leave the non-collapse case, let me say a little bit more about epsilon regularity theorems, which is closely related to the previous discussion. So just let me make it a little more explicit. So a classical one, right, was if you assumed that this is the scale invariant power of the curvature tensor. If that was sufficiently small, I guess this is assuming bounded Ricci and non-collapsing. So here we've normalized. It's important. You don't have to say non-collapsing really, but you have to observe that I've normalized this by the volume of the ball. That's a better way to say it, as Mike has emphasized to me. So it's not, the volume of the ball could be arbitrarily small, provided the integral was correspondingly small, and then you have a pointwise bound on ball, say, of half the size. So there were some generalizations in a similar spirit. So there's an extra hypothesis that in addition to an integral bound, say you also assume that you're sufficiently close to a cone that splits off an appropriate factor, and in our paper with Toby and Gong, so from 2002, we were just looking again at the L2 case, and but for the same reason as mentioned before, because there was a slicing argument and you needed some boundary term and the slice to have a non-zero invariant before you would get a contradiction. So there were some exceptions. In the Kahler case, the invariant was a simpler one, and just like the volume, and there were no exceptions, and more generally, none for special holonomy. So this was done in the paper with Gong from 2005. Now, by a quite different argument, assuming a two-sided bound, Chen and Donaldson proved an epsilon regularity theorem in essentially the above situation with no exceptional cases. So the argument was quite different. And in truth, I don't completely understand it, but that's my shortcoming. And anyway, it's very different. In any case, it's very, very different from the kind of thing that we had been doing. And as I said, there were some epsilon regularity theorems with LP bounds, just assuming a lower bound on Ricci, again with some exceptional cases, and this was in a paper of mine from 2003, which also proved rectifiability and so on. And maybe So I was quite pleased with that paper at the time. Maybe a lot of it is now, you know, obsolete. Maybe not all of the techniques. I don't know. And in any case, so here's a problem to get rid of the exceptions in this LP bound with just a lower bound on Ricci in this epsilon regularity theorem. So this is, I mean, it's pretty technical sounding, admittedly, but the arguments, both in the paper from 2003 and certainly in the Chen-Donaldson paper, are quite non-trivial and interesting, I think. And so I thought I would mention this despite its being technical. It's worth mentioning because maybe there's even some other argument where the argument itself would be interesting. Okay. So now I want to go to the collapse case, and with just a lower bound on Ricci. So this was in one of the papers that we did, or one or two of the papers that, or maybe even three. There was a sequence of 3 papers with Toby. The first one was in 1997, and then there were 2 in 2000. These were in JDG. So you can make some general statement about the structure in the collapse case. So you can not only, so collapsed means the dimension drops in the limit, or you don't have a uniform lower bound equivalently on the volume of the ball. Let's say if it's a pointed limit, if it's going to 0, then it's actually true that the dimension is at most n minus 1 if it's not n. I didn't put that up here. Now, the volume is going to 0, but one can renormalize it just by dividing by the volume of the ball of radius 1 about your base point. And then, in some weak sense, measured Gromov-Hausdorff sense, you can take a limit of a subsequence of those measures and get what we would call a renormalized limit measure on the limit space. So, I mean, you could also wonder about Hausdorff measure. This one is, so maybe we'll come back to that point. But this one is good because it's clearly doubling and so on. So it inherits some of the good properties that you would have in the smooth case. Now, it's actually interesting. Okay. So the regular set, defined more or less as before, which a priori could have pieces of different dimensions. In the non-collapse case, it's all of dimension n, has full measure with respect to any of these renormalized limit measures, and the singular set has codimension 1 with respect to the measure. So that's a well-defined, slightly technical notion that I won't go into. And the space is rectifiable with respect to any of these measures. So I'm not sure if I said everything I wanted to say about the renormalized limit measures, but here's a point which is interesting and not entirely trivial, that they're not unique exactly. That is, they're not determined, for example, by the metric structure of the limit. So to see that, you could imagine a line segment as a collapsed limit space, where you imagine it's the limit of cylinders with rounded off ends, right? So take a thin cylinder, cap off the 2 ends by adding a sphere, smooth the metric, let the radius of the thing go to 0. So then you get a line segment as the collapsed limit, and the natural measure is just Lebesgue measure. But you could also get that same line segment as a limit of take some cone with a very small circular cross-section and then round off the end of it, right? So it's also the limit of this kind of sequence of needles, so to say, were capped off needles. So there, the renormalized measure would be something like it had density x dx instead of just dx. But what is true, it was actually, I gave a talk about this at MIT, and Dan Struck asked this question, and then we showed it was true, that the measure class, even if the measure itself isn't unique, the measure class just depends on the metric structure. So in particular, when we say that the regular set has full measure and it's rectifiable with respect to the measure, that's independent of which measure we're talking about. And then there was outstanding progress made by Toby and Aaron Neighbor when Aaron was just a postdoc. So we had conjectured, Toby and I, that the dimension of the regular set was actually constant and it's basically connected. So one example that you could get, actually, it's a little counterintuitive, looks kind of like a horn, or we called it a trumpet. It looks like it shouldn't have positive curvature because of this. The geodesics don't extend uniquely and so on, but since it's a collapse limit, you could get something that looks sort of like a trumpet. And then we wondered, suppose you attach a line segment to the point of this trumpet, the point being where you would put your mouth, could you get that? So that is, could you have part of this collapse limit two-dimensional and another regular part that's one-dimensional? And the answer is no. And we understood that this is closely related to the issue of whether the isometry group of a limit space is a Lie group or not. And this, as we understood from work of Fukaya Yamaguchi in the case of lower bound on sectional curvature, is related to the issue of a kind of generalized Margulis theorem, whether you look at the image of a small ball in a space, in a manifold, say, with Ricci bounded below, the conjecture was that that should be nilpotent, or almost nilpotent, whatever, infranil. And that seemed to depend, if you wanted to follow the Fukaya Yamaguchi methodology, on knowing that the isometry group was a Lie group. In fact, initially we thought it didn't, but then we realized it did. In the non-collapse case, Toby and I proved that the isometry group was a Lie group, but there was something missing. So the way you can think about this issue is, so there's a classical result about maybe a locally compact group being a Lie group if it doesn't have small subgroups. Now, what would be an example of something with small subgroups? So you could imagine a circle, and then at one point you attach a circle, let's say, of half the size, and then another one of a quarter the size, and you pass to the limit. So now any of those circles you could kind of reflect, keeping the attachment point fixed. And since you have circles that are arbitrarily small, you would have arbitrarily small subgroups. So that wouldn't satisfy this condition of no small subgroups. I guess this is maybe Montgomery and Zippen's theorem, or maybe also Gleason, I'm not sure. But anyway, we understood that basically if you knew this, and that this was connected, essentially, then the argument in the non-collapse case would show that it's a Lie group, and that's what they were able to prove in a quite remarkable paper. So here are some open problems in the collapse case. So one of the embarrassing points is that, so this is a good problem. It's known, let's say, a lot is known about it in the Kahler, let's say the Calabi-Yau case. In general, you would like to know that for these collapsed limit spaces, they're actually manifold points. It's kind of analogous to the issue I mentioned before about singular sets, so this is not known. What is known is rectifiability, And there are some things which you might imagine that don't seem like they will work to prove this. And I don't think that it's known in general in the special holonomy case. Is that right? Yeah. There are definitely a lot of work in the Calabi-Yau case where it is known. But so this could be a good problem and might well be true even in, let's say, the bounded Ricci case. And then there's another embarrassment, which was right from the beginning, that the singular set has codimension 1, so that's a sensible notion. I won't quite go into it with respect to this renormalized limit measure, but in the sense of Hausdorff dimension, I believe, as far as it's presently known, it's not known that the Hausdorff dimension of the singular set is, as you would expect, smaller than the regular set. So this has been an embarrassment from the beginning and an indication of what I believe is still not understood. So there's still a lot to understand about the collapse case. Now we come to another remarkable result, which is nonetheless an epsilon regularity theorem in the collapse case. Aaron and Rubing Zhang. So, what? Yes, he's here in the audience, so he can correct anything that I say wrong. So I'm trying to say as little as possible. So this is actually not the full strength of what they prove. So this is a ball in RK. Actually, you can more generally imagine, say, a three-dimensional limit space across an RK. That is, you can eventually promote what was done in the non-collapse case to a somewhat more general statement than this, but I thought I would try to make it a little bit less technical. Okay. So it's kind of, in a way, analogous to Mike's theorem in the non-collapse case. So you assume that you're sufficiently close to a ball in, let's say, RK. Okay. So then the first statement is that...
So you only need bounded.
Yes. What, did I say something wrong? Oh, right. Okay, you don't need this, is what you're saying. Yeah. Right. So, okay. So then this is very close to the version of the generalized Margulis lemma, which had been conjectured far enough back by Kromov. So nilpotent of rank n minus k. But now the crucial thing is if it's actually n minus k. So this epsilon regularity theorem has also a topological hypothesis, which of course is not relevant in the non-collapse case or would be empty. And then on a ball of half the size, the curvature has a pointwise bound. So, yeah, this part especially, I think, builds on work of Kapovich and Wilking. And particularly for this crowd, you can notice it's consistent with, say, this famous Gross and Wilson example, right? They have a collapse to a limit space, and the limit space has some exceptional points where it's not smooth, but those are the points where you have some collapsing topology, and away from that the metric looks like a product, and you're in this case where the curvature is bounded. So this is another remarkable recent development. And okay, so now the last thing I wanted to mention was a different discussion of epsilon regularity in dimension 4. So this was from a paper with Tien in 2006, and there were various kind of applications of the main idea, but basically the main thing is this, that in dimension 4, if we go back to this idea of the L2 norm with bounded Ricci, then you have an epsilon regularity theorem, and the difference between the previous one is the hypothesis is not just small with respect to the volume, it's just small. So this is some delta n, which I don't, yeah. Well, it's, n is 4, so it's some delta. Okay. So, yeah. So this, this of course built on earlier work of Mike, and it involved various things. And although I won't go into the details really, part of why I put them up is to emphasize, one, that it did involve various things coming together, and two, that most of it actually did not depend on dimension 4, but then a certain part. See, one of the things is that in the collapsed region, you have something which you could, it's called an N structure or F structure. In any case, it implies basically, you could think of the simplest case as a circle fibration. So the Euler characteristic of the collapsed part was 0. And that would be true in any dimension, okay? And then that Euler characteristic gets paired with the fact that in dimension 4, the Gauss-Bonnet form bounds the pointwise norm if you have a two-sided bound on Ricci, the pointwise norm of the full curvature. So that's the annoying, shall we say. I mean, it's well known it's annoying. That's the part that's special to dimension 4. So most of the proof works in general. The last part even involves, in a slightly subtle way, the volume cone versus almost volume cone implies almost metric cone. And actually, for cones which can be arbitrarily thin, but the hypotheses are such that it still applies because the volume behavior is comparable to the thinness. So, but then at an essential point, this comes in, and that prevents anything in higher dimensions. So the last point is to what extent kind of using this, staying in dimension 4. I mean, when we did this, we were quite optimistic. Maybe one could really classify Einstein manifolds in dimension 4. That was probably overly optimistic. There has been a lot of important progress in the meantime, just actually independent of what we did, but in cases that are related to the ALF case and with some hypotheses, whereas what we did was completely general. I mean, then we had some plans for extending it to different kinds of volume growth at infinity and some very partial results. And at the workshop in March, we got enthusiastic again, and then, as before, proceeded to apparently drop it for the time being once again. But because this is completely general, one can certainly hope, although it's not completely trivial, as we found out, that one can do more with it in the general case. And then the last question is whether, despite what I said about Gauss-Bonnet in dimension 4, is there any possibility, because the rest of it doesn't depend on Gauss-Bonnet, is it conceivable that you could generalize it or part of it or something to higher dimensions? Okay, so I'm going to stop here.
3, do you mean classify Einstein for manifolds which are sufficiently close to a lower dimensional limit space?
Well, I mean, it's maybe said in such generality. Let's assume that the L2 norm is bounded, or the Euler characteristic is bounded, so we don't have like your example with Kronheimer and Claude. Okay, so where this discussion applies, let's say, but without assuming Kahler or strong assumptions about volume growth or how the curvature decays at infinity. Maybe some assumption about volume growth. There are some natural cases. Well, let's think about non-compact. I mean, at some point we were having, when you have, so the interesting part is where you have an F structure, right? Because now you know that most of it actually has bounded curvature, an F structure or an N structure. So in the limit of that, or close by metric on the collapsed part, you would have an invariant metric. So under this structure, maybe you'd have to prove, if you wanted it, absolutely Einstein, but see the point. So we had some conversations or some correspondence with Robert at that point, right? Robert Bryant, about Einstein metrics with symmetries. I mean, various people have studied that. It's true, Calderbank and maybe some collaborators. So, yeah, so I mean, if you just kind of imagine something at infinity and the rank of the structure at infinity, which isn't maybe necessarily constant either a priori and so on, but, something without more special assumptions. What else can you say? It's clear that you should be able to say some things, right? Anything we looked at, and we thought about it for a while, and then it sort of went away, turned out to be not so trivial as you might think. And then with extra hypotheses, people have said things. So pointing to, without real extra special hypotheses, like how the curvature decays or things like that. What else can you say?
I wasn't sure what you meant by or in the context of this the gross little term, etc.
When here or previously?
I understood previously where
Yeah.
you have a topological.
Well, what I meant is in the non-collapse case, for example, there are epsilon regularity theorems where other characteristic forms come in. So something like that. But unfortunately, what's true is on the collapse part, you always, the Euler characteristic basically is 0. That is, you have this circle, generalized circle action, right? But that's not enough to make Pontryagin forms 0. They can kind of be anything depending on what it looks like. So so that's a problem. But nonetheless, is there something? I mean, I don't know that there's a reason to believe that there's something you can do, but maybe worth thinking about anyway, despite it's not being obvious, because there was a lot else in the argument, and that all was not dependent on dimension 4. So I don't know if that's a good reason or not, but anyway, it's a true statement, I think.
And it seems like just if you only have Einstein with a circle symmetry, but it's not like a Kahler.
Yeah.
That's the wildest for the 4-dimensional thing.
Yeah, right. I mean, the more symmetry, the better, right?
I don't know what.
Yeah, well, yeah. So, I mean, maybe there'll be more papers by Chen and Chen, right? But they have some extra assumption in them. So, basically, I'm asking what else can you do without extra assumptions, but just by pushing this further.
Before you mentioned you could generalize with Minkowski.
Well, I mean, there are sort of maybe two answers to that. One is that it's a relevant notion because lower bound on Ricci implies by this Bishop-Kromov inequality that the metric is doubling, right? Which means that you can, if you look at so we're for the moment interested just, let's say, in balls of radius less than some number. So if you double the radius of a ball, the concentric ball can be covered by at most a definite number of balls of half the size. So that's a consequence of this Bishop-Kromov inequality, which is a consequence of the lower bound on Ricci. This doesn't need collapsing. Now, that doubling fact is what leads to Gromov compactness, which, then you can imagine taking limits of bad examples and studying the limits and using what you find out about them to go back and learn more about what they were the limit of, and so on. So because of Bishop-Gromov, that's where the possibility of taking weak limits in that sense is exactly what comes in, and that's Gromov's compactness theorem. So that's on the one hand, but on the other hand, if you don't, I mean, it turns out that there are other notions of dimension, right, which if you haven't thought about them, you probably have only the vaguest ideas about until you actually think about. So if you have something, let's say the singular set we're talking about, when you're talking about it's being small in the Hausdorff measure or dimension sense, you're trying to cover it, but you're allowed to use balls of different radii, and then you let the radius go to 0 and so on. But these more precise statements are, for example, about covering it with balls of the same radius and not even having to let the radius go to 0. And then there's some even stronger statement about packing. So that's sort of the Minkowski discussion. And then there's packing discussion. So in controlling the singular set, once you've talked about these limit spaces using Gromov-Hausdorff convergence, then if you can make a stronger statement about the singular set of such a limit object, of course you would like to make it.
So Hausdorff is sort of naturally occurring from the scale.
Well, Hausdorff is just the easiest to work with, and there was this. That's what was used classically with this same kind of technology of stratification and blow-up arguments. So, since it's the weakest notion, it's the easiest to prove something about it. And these earlier results, that is not the relatively recent ones, were all about Hausdorff measure, except for what I said about the open problem in the collapse case, in the non-collapse case. And they're proved by iterated blow-up arguments, but now there's a more effective version of that discussion, and that's what leads to this Minkowski or packing statements.